University about reverse decomposition of unipotents.
Thank you very much. I would like to thank the organizers for the invitation to give a talk at this excellent conference. It's the first conference I know which takes place in 3 different locations, not even 2, but 3. It's my first time here, actually. But the previous one, for 70 years of Ernest Borisovich, was taking place at the Independent University of Moscow, as far as I remember all of it. And that was also an excellent conference. And of course, for me, it's a great pleasure to be here because Ernest Borisovich was sort of one of my, he influenced a lot my interests, and he was one of my teachers in absence, so to say, and played huge role in many things I was doing. And one thing that I would like to mention, my talk today actually is related to the talk by, as you will see, to the talk by Alex Lyubotsky yesterday. And what I would like to mention is that Ernest Borisovich, he really concentrates on things. When you are telling him mathematics, he's sort of, he's very fast. And in Bielefeld once, I had a result in which I thought, in which I couldn't believe, and I was talking to various people and asking them to find a mistake in my proof. And at some point, Ernest Borisovich came there to Bielefeld. This was many years ago already. And I started telling him this proof, and he immediately asked why this is correct. And I thought that was the mistake. And later, we, with Alexander Lozgaryov, corrected that mistake, but of course, the correction was much, much faster, the answer, and published that with thanks to Ernest Borisovich for pointing out the masters. So what I'm going to tell you today is a recent sort of advance in the structure theory of Chevrolet groups at this point. Well, at the end, if I have time, I'll mention possibly generalizations. But to start with, I will start with the context of Chevrolet groups, split groups, but over an arbitrary commutative ring. So yesterday in Divostok, we've seen I think something quite hard. A large part of what we were doing in St. Petersburg was removing this extra stroke, you know, in R. So for us, R is an arbitrary commutative ring. Commutative ring. And of course, phi is reduced. Well, you can assume irreducible root system. And of course, I think of a Chevrolet group as the group of points of an algebraic. Not as something generated by something else, but as the group of points of an algebraic. But of course, everyone who works over a field thinks of this group, at least in the simply connected case, as the group generated by something, by some elementary generators. So actually these elementary generators, okay, they generate what we call the elementary cell. So these guys are the elementary generators that correspond to the roots of the root system and are parameterized by the elements of the ring. Okay, and what is the decomposition of unipotents? What are the main results about these guys? So the decomposition of unipotents is, well, you look at something like this. Where G is an element of the Chevalier group. Okay, I will state the result in a second. And this is, I think, these are results on which I've spoken many times in Unifit, among other places. But today I will speak about a new thing, about this thing.
What is E again?
E is the elementary subgroup.
It's a subgroup, it's not an algebra, it's a group. No?
No. It's a Chevalier group. That's a group of points of an algebraic group.
Okay.
It's a subgroup, of course.
Okay.
Actually, the only proof I will be able to give is for the special case where phi is equal to AL, and in this case, the Chevalier group is something like SL L plus 1, and the elementary group is something like this, and actually these results are already new in this case. So if you do not know what a Chevalier group is, then just look at this example. Okay? Well, what are the typical results? So here, the typical result is that, well, of course, you have to exclude rank 1. You have to assume that the rank is at least 2. And in this case, typical result is the theorem which is due to Suslin, well, the initial groups. Then, of course, it was generalized many times. Suslin Tabek and Tabek is that the elementary subgroup is normal in the Chevalier group. And of course, in St. Petersburg, we, as I mentioned, we like results that start let R be an arbitrary commutative ring. Okay, so here, this result was proven for this case by Suslin in 1976, and it started with, of course, it came as a surprise at that time.
Rank at least 2?
Huh?
Is the rank at least 2 for
The rank is at least, the rank is at least 2. This is what I said. Of course, it's not true for SO2. Okay, and what's the counterpart of this for this sort of factor? It's the theorem which has so many authors. I cannot list all of them. Probably I'll put dots. John Wilson and Igor Golubchik, who proved it for this case. Okay, and then many other authors, and then Abe, and then again many other authors, and then Wasserstein, and then something like this. What's another sort of major result at the level of K1? Such a result is that the description of subgroups in this group normalized by them. Okay, so description of E phi R normalized subgroups of G phi R. And this description looks as follows, that of course over a ring these groups are not simple or not close to simple, because they have normal subgroups that correspond to the ideals. So if you have an ideal, then of course, since this is a functor, you have the reduction homomorphism. Okay, which is not an epimorphism, but the group of points, of course. But it has a kernel, and you know that kernels of homomorphisms are usually normal subgroups. So that's a normal subgroup, which is called the congruence subgroup of level I. Okay, congruence subgroup of level I. So that's the reduction of level I. And of course, then you can take the composition of this guy with the now quotient model of the center, so a map to the joint group of the corresponding type. And then the kernel of that composition is called CRI. This is the principal congruence subgroup, and that's the full congruence subgroup. But there is also another guy, the analog of this guy. Namely, you can now span the subgroup by the elementary generators. Okay? Sorry. Elementary generators, not all of them, but those of level I. But of course, this guy, as here, doesn't have chances to be normal there. So to give it this guy such a chance, you have to take the normal closure inside the absolute elementary subgroup. So this is called the relative elementary subgroup. So it is generated by these guys as not as a subgroup normalized by E. As a subgroup, it's generated by something more. Okay, well, maybe I should mention that theorem, which is due to Stein, Titz, and Wasserstein, asserts that as a subgroup, this guy is generated by the elements that we denote by Z alpha of psi zeta, which are X alpha psi, X minus alpha zeta, the conjugates, where psi is in I, and zeta is in R. And alpha, of course, is in phi. Okay, so you do not need just, you need more than the elementary generators, you need their conjugates by the elementary generators, but the elementary generators of absolute level, not of level I. Okay, and of course, this again is only true when the rank is at least 2. Here again, the rank is at least 2. Well, in all of these results, if you wish your result to start arbitrarily different, then of course you have to assume that. Okay, so then, with this notation, roughly, the description asserts that for any H, which is a subgroup of G3R, normalized by E3R, there exists a unique I, an ideal, such that this H contains the relative elementary subgroup and is contained in the full congruence subgroup. Well, but of course this is not true as stated. It is only true when 2 is invertible in R, or sometimes 2 and 3 are invertible in R, when you have multiple edges in the Dinkin diagram. Okay, for simply laced root systems, it is true for elliptic elliptic rings in this form, but not otherwise. Okay, these are sort of the major structure results, which have various proofs, but what they assert effectively, what's inside there. Okay, so what does this guy assert? This guy asserts something as this. So you take an elementary generator, you take its conjugate, and it must be elementary. What it means to be elementary? To be a product of elementary generators. Yes, but what's the length of that product? Okay, consider the EL, VR, these are products of not more than L elementaries. Of course, this is a subset here, but not a subgroup in general. It is a subgroup only when you have bounded generation. So it is a subgroup. It means that actually E coincides with that guy. And this is called bounded generation, which you only have essentially for zero-dimensional rings and some one-dimensional rings, not otherwise. Okay? Here, what happens is that what you wish to prove that this guy belongs to some of those guys for some L, some fixed L. And of course, at first, it's not clear why it should be true at all. Because as I mentioned, for rings of dimension 2 and more, in general, this guy doesn't coincide with the whole elementary guy, so why this is true at all? Of course, for SL, the first proof by Suslin gave a bound, which was, in the case of AL, the bound was L times L plus 1 times L plus 2. Okay, but then, for other types, for exceptional types, for instance, this proof used localization. And of course, localization doesn't usually give you nice bounds. It gives you bounds that depend on the dimension of the ring. Okay, at least. And they may depend on other things, such as partitions of 1 in your ground ring and so on. So you can prove finiteness, but you do not get nice bounds. And the idea, which was proposed by Alexei Stepanov, essentially back in 1987, was that he gave another proof of Suslin's theorem, which gave the bound for the case of AL, the bound L equal to 4 times L plus 1. And immediately after that, I observed that this works also for other classical groups. For instance, for DL, you get the bound 4 times 2L times 2L minus 1 times 2L. Okay, and most interestingly, later, the idea was announced in our paper with Plotkin and Stepanov, and then much later I've taken care of all the details to get the explicit polynomial formulas, for instance, which in these cases give you the following bounds 4 times 16 times 27, and here 4 times 27 times 56. And everyone who knows the exceptional groups recognizes the numbers. So these are the dimensions of smallest representations, and these are the dimensions of the largest abelian radicals. Okay, so this is based on parabolic reduction in the corresponding representations. Okay, and there are similar bounds for other cases, which are more complicated or came later, but there are in this case. And that's amazing because, look, you take G, which is not elementary. For arbitrary elementaries, there is no bound. Even if G is elementary, there is no bound on its length. You take a conjugate of an elementary generator by something which is not elementary, and you always get something that is not just elementary, which is very, very short. Okay, I can tell you how short it is by observing the following thing, that as far as the order of growth of these guys, you cannot improve this much even over fields. Because what it means over fields? Over fields, of course, for the simply connected case, every matrix here is a product of elementary generators, as we teach our students in the undergraduate courses of linear algebra, but how many of those? Okay, and of course the best possible general bound is that over fields, this guy, well, the simply connected one, over K, over a field, is the product of u times u minus times u times u minus. Okay, which gives you 4 times the number of positive roots, which in the case of AL will be exactly this. Will be 4 times L plus 1 over 2. So actually this bound is essentially the same as the bound for fields. It's just twice longer. Okay, so it's a very, very good bound. And this I've taught many times at various conferences. The idea of this, if I have time, probably I'll explain you how this works. Because now we come to the counterpart. Because the counterpart is what we should do here. Here we should do this thing. So we should take an arbitrary element in the Chevalier group. We should look at its elementary conjugates, well, plus minus x actually. Okay, where x is an elementary matrix. Okay, and minus x, of course, means that it's the elementary conjugate of the inverse. Okay, so you have these guys, and what this theorem tells you is that as a product of those guys, you can eventually get the elementary generators of the level of this guy. You can get the elementary generators of this group. But how many? Until this year, this was not known. And this is a very, very special case of that. Was exactly what was mentioned by Alex yesterday. Because in Alex's talk, the arbitrary commutative ring was Z, the ring of integers. Of course, the group was the special linear group. And he was getting not an elementary generator of this guy, but some non-trivial elementary translation as a product of a bounded number without a specific bound of the conjugates of this guy. But this spring, Raimund Preußer, whom you probably know, he was a PhD student in Bielefeld. Raimund Preußer, in April this year observed that actually our computation from our work with Stepanov that gives you this, after some twist, it gives you also the other thing. You can read it, the computation the other way with some twist and get the bound. And after looking, he gave the bound for classical groups, which is a good bound for AL and DL. It's much worse for other classical types, for BL. For BL he doesn't give it, for CL he gives a bound that is much worse. But after looking at that this summer, I've noticed that also our computation for exceptional groups also gives you exactly the same bound for this problem. So here is my version of Brenner's lemma. So I don't think we need this anymore. So now we can state the theorem, which is essentially for, as I said, for AL and DL is due to Preußer, for EL it's mine. So the theorem is as follows, that you look at phi of type AL, DL, or EL, and you look at a matrix from this guy in the minimal representation. In the minimal degree representation. Okay, which is, I'm looking at the biomodule, not the, I'm not concerned with the fact that something can be reducible. So I'm looking at what? At pi 1 here, pi 1 here. For E6, it's either pi 1 or pi 6. For E7, it's pi 7. And for E8, it's pi 8. So here, these guys are the weights of the minimal representation with multiplicity. So of course, only case where multiplicity occurs is the joint representation of the 8, right? The zero representation, the zero weight has multiplicity 8, so we'll look at these guys. Then the X alpha G lambda mu, where lambda well, for zero sometimes you have longer things. So let me take lambda and mu non-zero. For zero you will have longer product. Non-zero such that their difference is, say, is a root, is a product of 8 conjugates, elementary conjugates. Of G or minus, G or G to the power minus. So now observe the difference with what Alex mentioned yesterday. So R is energetically different. Okay, and it's not just some guy, but it's exactly the entry of the matrix. Okay, and it's a product of not as some bounded number, but exactly 8 conjugates. And 8 is not mysterious. 8 is 2 to the power 3. So 8 is just because you get this guy as a result of computing 3 commutators, nothing more. You get exactly this guy. Okay, so this is much more precise, and I will try to mention why we need this, but first, how the computation itself works. Okay, so the computation itself, and again, you have also bounds for other cases. Amazingly, for this problem, for CL, the actual bound is better than these bounds. It's for CL about the bound which I erased plus something of smaller order, plus something of order L times log 2L. So something that is, so for CL the product is much shorter. CL over arbiter community free, this conjugate has exactly the same length, well, essentially the same length as for fields, but here it is not known. That's why I'm not stating the current result, which is ridiculous, which is something like for the long root, something like 1600 to start with, plus some free term. A very bad bound. I'm convinced that you can get much better than that. I haven't yet had time to think about it, to try to improve it. But how does it work? So what's the idea behind this? It's, sort of extremely useful, and Alex is not here, otherwise he would confirm my quotation from the Bible, which I cannot translate into English, which someone maybe will. Камень, отвергнутый строителями, оказался краеугольным. The stone rejected by the builders turned out to be the cornerstone, or something like that. Okay, and that's exactly what happened here. So how does this then decomposition of unipotents work in our paper with Alexei? So it works as follows. It starts with a fundamental observation that in a commutative ring, you know, any two elements satisfy this equation. Okay, which is an observation that was missed by many who were studying the problem. Okay, look at the matrix from SL. Look at the first column. Say, of course, you can apply this for any column. And here is exactly the place where we are using the fact that the rank is at least 2. So actually there are at least 3 of those entries. And now let this entry be A and this entry be B. Then you add this guy here, and you add this guy here with this coefficient. Okay, and then that's your matrix G. And what you do, what you get, well, because of this equation, the first column is not changed. Okay, so this means that the commutator of G minus 1 and T1, 2, B, T1, 3 minus A, that this commutator is in this parabolic subgroup. Okay, and then from a parabolic subgroup you can extract anything. So if you get a transaction which is of that shape, of course that's a product of 4 times L minus 1 elementaries. You know, that's how you get these bounds. Okay, this is how we were using this method. So what Preußer observed is that actually, then of course it was a huge technical problem for more complicated cases, like for exceptional ones, to prove that what you get there after some computations, is that you get your entry, but you get your entry with some coefficient that is usually something like in order to minor in other entries, and you get this for, then you vary your column, you vary your rows, you vary the row to which you add, and varying all this, you get your entry times some minors, and you have to verify that eventually you get enough of those to generate the unit ID, because your matrix G is invertible. But Preußer observed that you don't need it. What you need is that instead do what we avoided at all costs, namely take the commutators which bring you outside of the parabola. Okay, so you do the same, only that, well, you can do it with the second column, or you can do it with the, I will do this with the second column instead. Okay, sorry. With the second column, and then you do exactly the same. Then, as a result, the second column is not changed. But there is an extra factor which puts something there. But after the first conjugation, you get here 1, and this extra factor exactly equals B. So this commutator will have the shape 1 and then B here. And this B is actually the entry G32 of your matrix. And you get zeros here. So as one conjugation, you get a matrix that gets the entry of your matrix somewhere, and the rest is like it was in the parabolic. So it's something in the parabolic times an element from the opposite unipotent triangle. Okay? After which, with two further conjugations, you just get this guy. And since the elementary group is normalized by, since any permutation belongs to the elementary group, to the absolute elementary group, you can put this guy into any position. That's how you prove this result for the case of AL. Of course, for other cases, it's quite a bit trickier. So here you use the embedding of A2 in AL. For DL, you have to use the embedding of A3. For E6, you have to use the embedding of A5. For E7, you have to use the embedding of A7. And for E8, you have to use the embedding of D8. Okay, and of course, you believe me that it's, I do not have time now to show you, but otherwise, it's exactly the same computation, only that here, this computation takes about half a page, and here, it takes maybe 5-6 pages in the minimal representations, but it's exactly the same sort of stuff. And this is for this specific element, but actually, this allows you to estimate the length of any elementary generator where psi is from the lower, well, from the upper level of G. Upper level of G is the ideal generated by the non-diagonal entries of G and the differences of the diagonal entries. Okay, so any such guy, in those cases, is a product of not more than 4 times the dimension of G elementary conjugates, elements of this group. Elementary conjugates of G. So that's the effective version of the description of normal subgroups. But actually, you can go much further, because what you are really interested in, well, the description of normal subgroups is well known. What is less known is the description of the subnormal subgroups. And the technical core of the description of subnormal subgroups is that you have to find if are J normalized subgroups. Okay, and where J is another ideal. And this is sort of known for classical cases, but it was not known until recently for the exception ones. Okay, and this is our joint work with Zuhong Zhang Zuhong, where we do this for these cases. And well, let me state the result. And this amounts to the following: that you put X here, not the absolute, not the conjugates by the absolute elementary subgroup, the conjugates by the relative elementary subgroup. So technically, this amounts to this. But of course, you cannot express this from the upper level. You can express this from the upper level times this J, times this J to some power. And of course, the real sort of fight here is to improve this power. So the result looks as follows. And this result, as a corollary, implies immediately the description of subnormal subgroups. It looks as follows, that if H is a subgroup of GVR normalized by EVRG, then there exists a J, an ideal, I, an ideal in R, not unique this time. It's only unique up to something. It's not unique as such. There it was unique, here it's not. Exists an ideal such that this H is contained in CVRI and contains EVR I, J to some power. So what's this power? Well, for the case of AL, this has a very long history. Like Wilson has proven that in '73 that this is for rank at least 3. M is what was it? Was 7, I think. Was it? Yes. Then Bach has proven, like in 80, that it is 24. Then, well, of course, the smaller the better. Then Wasserstein has proven that it is 6. Then Lee and Liu have proven that it's 40. Then I have proven that it's 5. Yes, and then Wasserstein has proven that it's 4. Well, it cannot be 2. We still do not know, even for AL, we do not know that that it can it be 3 or not. But what follows from what I've just told you is that for AL, DL, and EL, you always get these bounds. And this is without localization. Wasserstein's proof is a very difficult proof involving localization. It is not implemented for other classical cases as yet with this bound. There the bound is like 8 or something. So with Zhang Zuhong, we have first proven this result with 7, then improved it to 6, and with this method to 5. Okay, and of course, since these are explicit formulas, they might have a lot of, well, a formula is a formula is a formula. When you have a polynomial formula, you can apply it everywhere. So I'm positive that this will give you a possibility to improve many other proofs on description of subgroups, and in many cases just write explicit formulas, replacing the elementary conjugates inside phi itself by elementary conjugates inside the subgroups, and still get such a thing. Okay, so that's work in progress. Very, very fresh. Thank you very much. And so
questions? No, then let's thank the speaker again.